again, yeah, so like Steve said, if you do have questions, feel free to just interject me and answer. We're not so big of a group that we can't do that. A little bit about myself. My name is Anna Hoffman. I'm a data and applied scientist on the Azure SQL team at Microsoft. Actually, interesting, I do live in Los Angeles, so I'm at home in Sherman Oaks today. And I work a lot on how we can move more people towards Azure, and also how we can kind of democratize AI and machine learning on top of our data platform. So today we're going to do a session called a behind the scenes look at ML, AI, and deep learning for data professionals. And this session is geared towards data professionals, and it's really done kind of in the light of SQL. So you'll see a lot of my examples are related to SQL. And at the end, we'll talk specifically about how this all can relate to SQL. Okay, so if we go ahead and get started, let's see, I can move through slides. So this is our agenda for today. We'll talk about data science and artificial intelligence and machine learning and deep learning, all terms that you've probably heard a lot about. And after this session, you can add it to your resume and say you're a data scientist. Not really, but hopefully at the end of this session, you'll walk away with a better understanding of how these terms are related and how they're different, and even a little bit of an understanding of how they work. And kind of the biggest goal for today is that you have a little bit of understanding how they work, and we'll actually get into some math, hopefully not too much math. Again, that's why you're allowed to stop and interject as needed. And at the end, we'll talk about some platforms and tools, and of course, I'll bring it back to SQL because that's what I do. So we'll start with data science. And when we talk about data science, it's really the combination of two things: data analysis, and this is something that I think most data professionals are very familiar and experienced with. And then data science also involves the scientific process. So this is that idea that you might remember from a very long time ago of the scientific method and creating a hypothesis and then either proving that right or wrong. Now, we can use data science to do things like artificial intelligence. And we'll talk more about artificial intelligence, but at the highest level, it's basically the idea that computers can mimic some sort of human behavior. And now within artificial intelligence, there's machine learning, and then an even more specific topic within machine learning is deep learning. Now, when we're doing any of these things, data science, ML, deep learning, it's typical we have to follow that process. And that process that we recommend is called the team data science process. And there's a link down in the lower left corner that you can see there for the TDSP. And basically, this is a process that we developed to take you through any data science lifecycle. So basically through any data science problem that you might have. And it has 4 or 5 phases that you can see. The main phases being, just to give the highest overview, is we start with business understanding. And this is understanding what question do you actually want to answer with this data science that you're doing. And many people argue, I would argue that if you don't have a question that's answer would result in some sort of action, then it's not really a good question or a good problem to start with. For example, if I'm trying to predict whether or not you're going to buy whatever it is you're looking at on Amazon today, if I know the answer to that question, so if the answer is yes, it would ideally invoke some sort of action. So maybe I would give you a discount, or I would suggest something else for you to purchase, or that sort of thing. So we want our questions to result in some sort of, the answer to result in some sort of action. And once we understand the question really well, we'll move on to getting the right data and understanding our data. And this is something that data professionals, I think, are probably very familiar with. And once we have a good data set, and maybe we've gone back and refined our question, we move to the modeling stage. And so what you'll typically do is you'll split your data into training data and testing data. And you'll basically select some sort of algorithm. And run data through it to train a model. And there's other things you see on the left-hand side here that you can do there as well. We won't get into those details, but basically you'll pick a model that performs the best among the testing data set, so data that hasn't seen the data before. And we'll talk more about this. And then you'll deploy that model. And as you can see, this is a very iterative process because things change, trends change, regardless of what you're doing. You're going to need to somehow update that model. Just checking if there was a question. No question, just people joining. Welcome. So talking a little bit about the data science lifecycle. Now let's see how, if we take a look at history, how have things changed over the years. And before we go any further, just a quick note to those of you joining us. If you do have any questions, just feel free to interject, and I'll try to answer them as best I can. So if we look at history, right? In the 1950s, around 1956, we as society started doing lots of research, and we decided, you know, we are so good at computers, we can predict how people will behave. So for example, if you have a kid and you offer them a burger or a salad, we said we know what they'll pick, right? They're going to pick the burger every time. So, you know, scientists, mathematicians, people working on this thought that this was something they could hard code in, this artificial intelligence. So any human type of behavior we could hard code in because humans are so simple. Well, probably not surprising to those of you on the call, that did not work out quite the way that they wanted it to. So then in the 1980s, after it going kind of dark in this area for a while, they actually call it the AI winter. Machine learning and really data mining became a much bigger thing. So using statistics a lot more, and we were beginning to get a lot more compute power and the ability to store a lot more data and process more data. So we actually became pretty mature in the machine learning stage. And then finally, and more recently, deep learning has become increasingly popular. And a big reason behind this is because the amount of data that we're not only generating, but able to process and store. And so again, just to give a high-level overview of these differences, artificial intelligence early on was just trying to mimic human behavior at a very unintelligent necessarily type of way. And then machine learning came around and was using mathematical formula to manipulate and process data to eventually learn and be able to predict different things. And deep learning is a specialized area within machine learning that uses layers of algorithms, which we'll talk about, to create some sort of prediction or classification. And another interesting thing is machine learning, typically once you hit a certain volume of data, your model performance will kind of plateau. So it won't get any better even if you add lots more data. Deep learning is different in this way because it typically continues to improve as you add more data. So that's kind of your high-level progression history lesson for today. Okay, so if we talk a little bit more about artificial intelligence, like I said, in the 1950s, they said something like human intelligence can be so precisely described that a machine can be made to simulate it. So what we did in the beginning, kind of talked about this, is we use symbolic methods. So things like expert systems, so a bunch of if-then statements resulting in some sort of action or logic or simulation. That's what we used. And over time, as we moved into the machine learning phase, we also started to get more statistical. So for example, inference is how they predict the weather. And really this field of artificial intelligence is very broad. And an interesting way to look at these or to actually start using these today is something called cognitive services. Now, this is something you might have heard of before, but basically what it is it's a set of APIs, and these APIs reference models that Microsoft Research has been working on for years, in some cases, 20 years, some of these text models and vision models. So you can basically just call these APIs and use AI. So you'll hear me talk about using AI or applying AI, which means you don't necessarily have to do or understand everything that's happening behind the scenes, but you can still take advantage of those additional insights. And these on the page, these are all the different kind of implementation families of artificial intelligence, but it just so happens these are also the different cognitive services that are available. And the distinction between blue and black font is that some of these cognitive services are actually customizable. So for example, you can use the language understanding cognitive services to create your own language understanding model. So we do all the back-end stuff for you, and you only have to know very little about creating this model, and you can create a custom model.
Is now joining.
Do we have a question? Okay. All right, so let's take a look at an example. And what I'm going to show here is a tool called Azure Data Studio. And I don't know if all of you have seen Azure Data Studio, but to give a brief background information on it, Azure Data Studio is something that the SQL team basically forked from Visual Studio Code. So you might notice that it looks pretty similar to Visual Studio Code in the way it's arranged. So we forked it from Visual Studio Code and created this thing called Azure Data Studio. So just a very brief 1-minute tour. You can actually add connections to servers. So for example, you see I have an Azure SQL database that I'm connected to here. You can use things called Jupyter books. So they have different workflows you can go through. I can do source control stuff here, like in GitHub, and I can manage files. So you can see right now I'm in a repository that I'll share with all of you after the session. Okay, and then what you're looking at here is a Jupyter Notebook. And Jupyter Notebooks, I think, are relatively new to the data community, but if you've worked with things like Databricks or Jupyter itself, you've probably seen something like this. A few things, Jupyter Notebooks always end in this IPy file format. And the interesting thing to me about Jupyter Notebooks is you can mix code with text. So I can actually run this code. So I can set the language to run in. This is what I have set up today. So there's a SQL kernel, a PowerShell kernel, Python kernel, etc. And I can connect it. So here I could connect to a database and actually run within that and save the results. So this is actually, and maybe a fun presenter tip, this is actually a notebook that I've run already. And so I can save those results and use them here. So that's my quick blurb about Jupyter Notebooks. What we were talking about was applied AI, as in specifically SQL. So you might have heard of this thing called machine learning services in SQL. And in SQL 2019, we added the capability to also use Java. And I'll talk more about how this actually works closer to the end. But for now, just believe me that I'm now able to run Java code, in this case, in my database, so without moving any data. Okay, so now let's finally look at a use case of applied AI in SQL. So this first example is for sentiment analysis in Java. And so what I have here is I'm using the wide world importers data set, and I have some product reviews. Now, these are all free form and maybe something that would be pretty easy to do or to think you might want is to get
is now exiting.
Is to get some insights on these reviews. So are they positive? Are they negative? That sort of thing. So what I did is I created a Java program. So I'm calling it here, creating an external library. And this is that Java compiled program. They're stored as jar files. And this program basically calls the text analytics cognitive service and returns a sentiment score. So I'm now running that on that same set of data, and I am now getting a sentiment score. So something really easy that, quick time to insights is doing something like this. And maybe now this action would determine whether I continue kind of in stocking this product or shipping this product. Another example, like I said, there are also custom cognitive services. This one is for LUIS, or the Natural Language Understanding Cognitive Service. And what I've done here is I have some delivery instructions. So the scenario here is I have some sort of shipping company and our truck drivers input their status manually. So on their phone, they just type in their status. So this is free form results. And you can see there's like a to location and a from location and some sort of date and time potentially that I might be able to get from this, maybe put some dashboard on it and see where everyone is and kind of track my fleet. So what I did is very easily, and again, I'll share all the resources for how you can do this, but I created a Lewis model as well as a Lewis Java program that can then take in those delivery instructions and spit out the origin, destination, and delivery date time. So you can see it was able to do that really well, even get out things like date from something as vague as Tuesday. So this is just one example. Again, we're going to show quite a few examples, so don't feel like you're supposed to understand all of these. I have dedicated sessions for each of the examples that I'm going to show today. This is really just to give you an idea of the realm of the possible. So before I go any further, I just want to take a quick check-in if we have any questions, insights, anything you want to share about cognitive services or AI in SQL.
I would like to share something that is totally off topic. Looks like we had some problem with MS Teams. It created actually 2 rooms. So some of the people joined that second room and there was no one there. So now they hopefully can rejoin this room. In any case, folks, this has been recorded, so we will post it on YouTube once it's ready from post-production. Sorry for the mess, I guess.
No problem, Steve. Thanks everyone for your patience. And if you've recently joined, you haven't missed too much. We talked about applied AI in SQL. We were talking about artificial intelligence, which to review for everyone is just this idea of mimicking human behavior. So if there are no questions, we'll go on to talking about machine learning. Again, if you're just joining this call, feel free to interrupt when you have questions. We do have a smaller group of people, so we are able to stop and take questions as needed. So if we think about machine learning, there is a formal definition. There's probably lots of formal definitions. This is just one of them. So a computer program is said to learn from experience E with respect to some class of tasks T and performance measure P if it's performance at T. Like, this is very confusing. Hopefully maybe some of you are seeing this as well. But I mean, this all checks out, but it's not necessarily the most easy way to understand how the heck machine learning takes data and turns it into insights. So let's look at a specific example, okay? Like this, a very simple example, okay? Let's say we have a bot, and this bot, this is what we're trying to train, okay? And we want our bot to be able to recognize cups. So if I just fast forward those, what you see is on the left-hand column, let's see if I can use a pointer here. So on the left-hand column, you see images. So this is my input, and maybe my question is the image a cup or not? So for these images, I have things called features. And a feature is basically a term that's equivalent to columns, right? Data scientists try to make things a little bit more complicated. Just kidding. But these features are basically columns of data that describe or that might give us an indication to what the label is. The label is whatever it is you're trying to predict. So in this case, it's just a true false, but it could be a number, it could be a color, it could be anything, a classification, and we'll talk about some of the different families in a bit. But what you can see is if we take this first cup, for example, or first image, the features is it has an open top, a closed bottom, holds liquid, and is hand-sized. So what we're going to do is we're basically going to feed all this data to our bot or to an algorithm, and we're going to use it to train this bot or train a model. And what it will hopefully be able to do is it might come up with a model that's something similar to this. And Of course, this is all in words and computers don't work in words, but this is just an example of what the model might come up with. If you were to come up with a model, what you might come up with for a cup. So if all those things are true, then it's probably a cup. So now what we can do once we've trained our model is show it something it hasn't seen before. So you'll notice from our images over here, it hasn't seen this blue, slightly different formatted cup before. So it would run it through its model, evaluate its features, and then determine a label. And in this case, it determines it is a cup, and it will also give you some sort of certainty or confidence level. So in this case, it's 90% positive that this is a cup. So that's our kind of one-on-one there. Now, there are many more things that machine learning can do, obviously, than just identify cups. So there are 5 main families of algorithms that are used in machine learning. Some of them are supervised, but we'll talk about those ones first. But basically, the difference between the supervised and the unsupervised, those are the 2 main categories, is that supervised models, we have a label. So if we think back to the cup example, we had a label of that it was or was not a cup, our training samples. In unsupervised learning, there isn't necessarily a label or an exact answer. So we're more trying to find trends or identify certain patterns. So that's supervised versus unsupervised. So supervised, we have the answer. Unsupervised, we don't. Okay, so within the supervised family, there's 4 main categories, okay? So when we think back to the beginning, when we talked about the team data science process, it's about answering questions. So the first question is how much or how many? And this relates to regression types of models and algorithms. And regression is probably one of the most commonly used. You might see linear regression very often, and it's usually a starting block when you start to learn about machine learning. We can also answer, is it odd? So are there any anomalies? An example of anomalies, identifying anomalies, is fraud detection. Another example is which category. So if we take in various features about someone, can we put them into a different box? In this case, it's just identifying birds versus bikes versus tools. But you would basically take in different features. So remember, features are just columns of data about that help you identify the label. Then there's which action. So this is more prescriptive, kind of what should I do next type of problems and questions. And this is reinforcement learning. And finally, this is that unsupervised one. And a good example of this is when I'm on Amazon, basically every day, ordering something new that I don't need. Amazon is running recommendation models in the background. And at the very bottom, you might see the section, you might recall seeing this before, that says customers commonly purchase these things together. So, you know, they're trying to get me to get that extra thing, which I probably am going to get. But basically, you know, that's an example of a recommender. So there's no exact answer. They're just trying to identify, based on my previous purchases, based on what I'm purchasing right now, what is something that's like it, that might go with it, that I might also be interested in. So these are our machine learning uses and some of the families. Now, when we talk about languages, you know, I debate about putting a slide like this up because there are lots of languages you can use do machine learning in. You know, believe it or not, you can use Java for machine learning or .NET for machine learning. Depending on the platform you're working on, you might use some sort of Spark R or PySpark if you're using Spark or Hadoop. Python and R are 2 really popular languages. There's a very common debate about whether or not, you know, if you're new to data science and you want to learn Python or R, which one should you learn? Everyone's going to have their opinion. I prefer Python. I think there are a lot of great libraries out there, but I also use R. So more often than not, it's not Python or R. It's just both. But anyways, so this is just an example of some of the libraries out there that make it really easy. Now, later when we talk about deep learning, TensorFlow and Keras have really nice libraries to make that easy, but today we're going to do it kind of from scratch, and I think that's important. Even if you're using libraries that do all the hard stuff for you, if you don't have a good understanding of what's actually happening, there's some missed learning and probably missed opportunities there. Okay, so let's take a look at machine learning. So we're going to go back to SQL, and this time we're going to look at Python. So you can see here I'm running in a Python kernel, just running it locally. And again, we talked about the in-database machine learning with SQL Server to use Java, but you can also do R and Python. And this example, again, I'm not going to walk through this entire example. I just want to give you an overview of what's possible and kind of some idea, right? So this is from the wine quality data set. This is a public data set. It's very popular. There are lots of very common public data sets that people use to learn machine learning. They actually have competitions on sites like Kaggle.com to see who can develop the best models based on some of these common data sets. But so this is the wine quality one. It basically has a bunch of information about different wines, so different chemical things we'll see in a bit. And then it gives a prediction on a quality score. So 1, 2, 3, 4, all the way up to 9, 9 being the best wine. Okay, so how this relates to SQL is what I'm able to do is using Python in my own environment, I can actually connect to SQL. I've taken out some important info here, but I can take that out. And what allows me to do this is something called RevoScale Pi. Now, RevoScale was an R company that built these RevoScale packages for distributed machine learning. So doing machine learning at scale on really big sets of data. Now, Microsoft acquired them a while back, and that's kind of where this R and Python integration in SQL came about. But they also developed these packages that allow you to use them from outside of SQL Server. So here, I'm able to actually connect to SQL Server and set the compute context to be SQL Server. So I could use my local compute, or I can use the compute that's within SQL. So that's basically what I'm doing here. I'm going to skip ahead a little bit. We talked about how after you have a question, so if we had to know what quality, predict the quality of a wine, so we determine what to stock in our stores, for example. The first thing we want to do is look at the data, understand the data. So here, I'm just able to run some queries basically and look at some of that data. So we see some of the various chemical attributes and then the quality. So this is what we're going to try to predict. I also did this for white wine, so just checking if there was any difference. A lot of times you'll see people make histograms or various plots so they can see the data not only statistically, but also visually. So this is just an example of this. Again, all this I'm going to share with you. So we're just flying so we can talk about different things. Okay, now what I want to show here is in order to create a machine learning model, what I'm going to do is I'm going to split my data. We talked about this at the beginning, but I'll split my data into testing and training. And why I wanted to show this one is I'm actually using one of those common packages, scikit-learn. I'm able to use that from within here, and how I apply that on SQL Server from Python is I basically write my Python code within a function. So this function is called split data. And then I can use those RevoScale packages. It starts with rxexec to call that function on a set of data. So on this query, using the compute of SQL and get the results back. So that's just one example. Now I could write anything in these. I could write lots of functions and apply them in database. This is just one example of how I'm able to use outside packages along with Microsoft packages in SQL Server. So there's some other things here I'm doing to prepare and train this model. We won't step through that. But once we have a model, then we can start making some predictions on the unseen data, so on our test data set. And you can see after just one iteration, we're doing pretty well. So this quality is the actual quality of some of those test samples, and this score is the prediction. Now, there's still some tweaking we could do here. You could look at how its R-squared score is. There's other things you could do. You would want to try to find other algorithms and test using different features, something called feature engineering, so determining which and how the different features or different columns affect the model or affect the outcome or the label we're trying to predict. For the purposes of this, we're not going to try to find a better model. But the last thing I wanted to mention is that you can, once you have a model you're happy with, you can actually use another package called SQL ML Utils, and there's the equivalent of this for R, to basically create a function. So this function creates that model, and I can use that function to create a stored procedure in SQL. So here I'm using create stored procedure from function. I'm giving the name of the stored procedure and the train model stored procedure, and then this will show up in my SQL. So whether you're a SQL person or a Python person, you can kind of use this, right? Because I could write this all in SSMS if I preferred, or I can write it here, or I can have my data scientist write it here, and then I can kind of okay it as the data person and then deploy it into my server. So again, just another, yes.
Quick question. So I see you using a connection, but you using a SQL authentication. Is this could be only SQL authentication, or it could be actual Windows authentication?
Sure, great question. So there are different ways of authenticating. Of course, this is probably, I think we could agree, not the most secure way of doing that. But yes, there are definitely other ways that we can do that and make this more secure. Just for the purposes of this, I just
got it. Okay.
Simple. Yep.
Thank you.
Any other questions about machine learning in SQL or anything that you've seen so far?
What do you consider to be the best tool as of right now? Using the RStudio or using SSMS or using Azure Data Studio?
Yeah, that's a great question. So Steve is asking, what's the best tool for doing machine learning in SQL, RStudio, Azure Data Studio, or SSMS? And really, it just comes down to preference. I think some of the notebook functionality that you get with something like Azure Data Studio is really valuable. But if you're more comfortable in your own Python IDE or something besides RStudio, at the end of the day, it's not really going to matter. The functionality is going to be the same. But personally, my preference is to use something like Azure Data Studio.
Got it.
Cool. That's a good question. And we'll talk some more about the different tools that are available as we get near the end. Okay, so now this is the part where it gets really fun. We're going to talk about deep learning. So just kind of to segue into that, machine learning is great, and machine learning gets us really far. For example, we could create a very good machine learning model to recognize this dog or various forms of this sketch of a dog. Now, where things get really complicated is when sometimes machine learning can't quite get us, that extra mile. So for example, myself, I travel a lot with Bob Ward and Buck Woody, and we were on a trip and we got to do this mini safari in South Africa. And we were trying to locate wild dogs. Now, this would be very hard for a machine learning model that was trained on dogs that look like this, or even real dogs, to find a dog that was a wild dog that was here. If you blow it up, you can actually see there is a wild dog in this picture, in this image, but even the human eye, it's hard to recognize. And that's kind of where this need for a method that could get better and understand more complex problems this need for deep learning. So we're going to walk through some math, like I said. Hopefully this takes you back to grade school, but also is familiar enough and doesn't overwhelm you, and we don't have eyes glazing over or people looking at other things on the internet. So just stick with me, and if you get confused or we want to slow down or go back, we can do that. So I say learning through layers, and why is that? So you maybe seen this before. This is what a neural network is sometimes depicted as visually, where these are neurons and these are layers. So here it looks like this is a 2-layer network. The reason I say that is because this input layer doesn't count. So really we just have a 2-layer neural network. So it's not really a deep learning exercise if it's just 2 layers, but you get the point. It's the same regardless of how many hidden layers we have here. Then we have inputs and outputs. So our inputs is going to be basically whatever training data we might have available. And all of this needs to be available in a numerical form. So part of your prep work is getting that in a numerical form, and we'll talk about that. And then once you get your data into the input layer, it will traverse through the layers. So your question next is probably, well, how does it do that? So if we take a look at one neuron, so let's just look at one. So let's say we're looking at this one right here. So what's happening is we're going to have inputs coming in. So you see things coming from the input to this hidden layer from all of the different inputs or all of the neurons in the layer before. And it could come from all of them. It could come from just some of them. That's another complication that you can add later, another complexity.
Anna?
Yes.
There is a question if you can please define what deep learning is.
Sure. Yes. So deep learning is, if you missed the beginning or if you're still working through that, deep learning is with a piece of technology within or a strategy within machine learning. So we have artificial intelligence, which is kind of trying to mimic human behavior. And then one layer within that, we have machine learning, which is just the generalized technique of using algorithms to make predictions from data given a certain amount of data. And then deep learning is a specific type of machine learning where we actually use something called layers. And that's these layers that we're talking about here. The reason I was saying this example is actually not so deep is because it only has, 2 layers, where sometimes these things have, many layers with different ways of traversing data through these layers. And what we're going to do now is actually walk through how deep learning works. So hopefully that helped answer your question, I think, Elena. If not, feel free to come off mute, or we can walk through this and then you can see if it makes more sense. Cool. Great. So what we were talking about is we have a neuron. So let's say we have a neuron here, and that's the same as a neuron here. Let's just say we pulled it out here, and we have different inputs coming in. That's what these arrows mean. Now, on each of these lines, you can imagine there's a weight. And at the beginning, this weight is just a random value. And we'll see that as well. And then this X value you see here is the input. So we basically take our inputs, we have some random initial weight, and now some math for you all is we're going to sum it. So what this is called, this is the equivalent of a dot product if you're familiar with a dot product. So what we're doing is we're going to multiply each of these together and then add it to the product of each of these, then add it to the product of each of these, and add it to the product of these, etc. Now, what we're doing here is we're actually creating a linear relationship. So if you remember the equation of a line, now if we were doing this in person, I would wait until someone could tell me the equation of a line. But just since this is remote and people are probably shy to come off mute, the equation for a line is y equals mx plus b. So that's what we're simulating here with each one of these paths is mx plus b. So the weight, which would be the slope, if you remember the m from y equals mx plus b. And then our input is the x, and then b is this bias term. Now, for whatever reason, in these diagrams and in these maps, they just leave out the bias term. But I like to remind people that this bias term does exist because it does kind of remind you of something you're familiar with when you're trying to create an equation for a line. Now, once we have this sum, what we do is we run it through an activation function. Now, there are lots of different activation functions. The one I picked today is sigmoid. There's also ReLU. There's lots of very commonly used activation functions. We won't get into the detail of why you might use one versus the other. But what you want to think about it is you have some number coming out of here, right? And what we want to do is basically, in terms of like a neuron, is we basically want to decide, should we fire the neuron or not? So what you can see is this running it through a sigmoid function. This is a plot of a sigmoid function. Basically gives it some answer between 0 and 1. And unless it's pretty close to 0, that answer is going to be pretty close to 0 and 1. So you can think of it of saying, like, should we turn this on or off? So basically a bunch of switches that we're turning on and off, so until we get to something that makes sense. But this first time around, it's going to be pretty random because all these weights are random. Sorry, all these weights are random. So this number might not mean much to us. But anyways, anytime you see an activation function, it's basically scaling your output between 0 and 1, and more often than not, making it very close to 0 or 1. Okay, so then that gives us an output. So what have we done here? What we've done is we've done one of these. Now remember, this is happening to each of these, and after we move through this layer, the output here becomes the input for this next neuron. So we'll basically do this lots of times. Hopefully everyone is following. But what they call this process is feed forward. So we're making our way forward through the neural network. And we're getting new outputs as we go along. Now at the very end, in this case, we have 2 outputs. We might just have 1 output. We might have 10 outputs. There's a lot of flexibility and complexity that can come in here. But at the very end, we're going to try to figure out, okay, how wrong were we, right? Because we just went through the model once, or the network once. So most likely we were probably pretty wrong. So what we use is something called the sum of squares loss. So how wrong were we equivalates to the term loss, right? And what this sum of squares loss is, just to make it disambiguated or clarify it, is it basically takes the difference between the actual output and the predicted output and then squares it. And then we sum those among the different outputs that we have. Now, once we know how off we were, we want to know, how is that loss changing, or how can we make the loss less? And the way that we do this is we take the derivative of loss. And this is the part where the math gets really quite ugly. Actually, the derivative of loss simplifies to something quite nice. But for the purposes of this, and for the purposes of, I recognize that it's been a long time since any of us did, probably this was calculus 2 or 3, or differential equations where you dealt with chain rules and that sort of thing. I do include a link to it if you want to go through it. But yeah, so basically what we're trying to find out ultimately is the derivative of loss. So how is loss changing? If you remember, derivative is basically signifies the slope, so how something is changing over time. And once we know how loss is changing, so the derivative of loss, we can know which way to move or which way to update our weights so that our loss decreases, so we can get to the minimum loss. So to simplify that, basically we take our old weights. So remember, those weights at the beginning are just these random numbers that we took in. So we'll take our old weight and use and add the derivative of loss, and this will bring us closer to hopefully a weight that gives us a lower loss. And so what we'll do is we'll do this at every layer. So here we'll work backwards, and we'll determine the loss, then the derivative of loss, and then we'll update our weights. And we'll do that for every single neuron moving back to the left. So that's why this process is called backprop, or back propagation. What we'll do is we'll feed forward. So we'll go through, and we'll calculate a new output based on the random weights. Then we'll go back prop, and when we go back, we'll update these weights, hopefully getting closer to the answer. And we might do this thousands of times, going forward and backward. Just checking questions. No questions yet. So that's kind of a nutshell of how this might work. So we'll go through this thousands of times till we get weights that are accurate. Now, there are other complexities that we can add here. For example, I said sometimes you'll actually turn off certain neurons on certain pass-throughs. You might also use different activation functions. And because remember, each one of these neurons has an activation function attached to it. So in different layers, you might use a different activation function. Hopefully I haven't lost everyone yet. The basics here is that we use basic linear understanding that we have. So this y equals mx type b calculations to create a linear relationship. And then we use something called an activation function to then fire these neurons or turn them on or off, which makes this a nonlinear process. And we repeat that through the layers. And then we go back to determine the change in loss and update our weights. And we just continue this on and on. We'll also see an example of this in code. I think there's a question.
Sure. Is it safe to assume that out of the three topics that you mentioned, the artificial intelligence, machine learning, and deep learning actually requires stats? Knowledge of statistics?
Yes. So I would say artificial intelligence, or this idea of using AI or applying AI, requires very little knowledge of stats. Now, as soon as you hop into the machine learning space, you're going to need to know some statistics to understand if what you're doing is valuable, if you're moving in the right direction. But yes, I would agree that as you move towards deep learning, this is where some of the math gets the most complex. But that being said, yeah, go ahead.
And this is because there are no existing functions? So
that being said, all of these things that I'm showing today, so the using AI we saw with cognitive services, the machine learning, and as well as deep learning, there are lots of packages and libraries available that you can leverage. Personally, I think that having this understanding from an at-scratch level at least helps you understand what you're doing when you're manipulating these. But 100%, you aren't having to actually derive the derivative of sigmoid or the derivative of loss on a regular basis if you're just using, TensorFlow or Keras or some package like that.
Got it. Thank you.
Yeah. Cool. So at a basic level, this is deep learning. Now, as things get more complicated, like I mentioned, one thing is you might add lots of layers. So if we take an example of a person, so we see this picture of a woman in the bottom left, we may want to identify not only that that's a person or a face, but we might also want to identify who it is. I actually don't know who it is. I don't know if it's anyone famous or anything, but that might be something we're trying to do. Facial recognition is a very real thing. Many of you use it to get into your phones or laptops today. But this problem becomes much more complicated because not only are we trying to identify features within the picture, for example, eyebrows or eyes or nose or mouth or earrings or that sort of thing, but we're also trying to put those pieces together in a way that makes sense. So this is just one example for facial recognition. Deep learning is very often used, but over many iterations, if you have enough data, so remember we're going feed forward and then back prop, and then we might be editing what's happening underneath. These layers might start to represent certain features. And brief overview, those features we talked about, features are, for a cup, for example, are open top, closed bottom, holds liquid, hand size. Now with machine learning, we had to supply these features to the model, but with deep learning, over time, it might actually pick out those features by itself. So you see there's edges. So first a layer might identify edges and then combinations of edges. So you see some of those combinations of edges might be an eye or an eyebrow or what have you. And then there's object models, and these might represent actual faces or of certain people. So this is a sophistication that deep learning can get. So if we get a little bit of understanding, we can make the machine do most of the work for us. So that's one of the big benefits of deep learning. Now you might be wondering, okay, how do we take this face and put it into a neural network to begin with? So what we do, and here's just an example, is, and this is also a classic example of recognizing handwritten digits. But what we do is we take an image, and it's common to put it into a 28 by 28 pixel measure. I'm not sure why that's the number, but that's a number. So what they've done here, if you look, is we took an image and we put it into a 28 by 28 shape. And then what we did is we assigned a number value or a color value to each of these pixels. And these number values will range from 0 to 255, which is the grayscale equivalent or what have you. So you'll see as we get closer to the biggest parts of the 8, we get closer to 255, which would be a white digit. So that's basically how we turn an image into numbers. And to make things more complex, if you have multiple colors in your image, then you oftentimes will have 3 layers of these 28 by 28s. So anyways, you turn your image into numbers, and each of those pixels goes into your neural network. But this is much more complicated and much more inputs than we saw in our original example. So hopefully it's coming to make sense to you, the amount of compute that is required and the amount of data that is required to get something out of this, because we're sending in 784 different pixels. It's not like the cup where we're sending in four different values or characteristics. So we're sending this all in and hoping that we're working to get the neural network to understand. Okay, so I want to put all that together with a demo. I hope you all are sticking with me, looking for questions. But in this demo, we're going to do not so deep learning. So we're going to do just a 2-layer network. But I think this will give you a better understanding. And again, on a daily basis, you will not have to write these from scratch. What we're doing is writing a neural network from scratch. Now, this is in Python. So here I'm running this one, Python 3 locally. And I'm actually going to run this one. The other notebooks I had already run, but this one will run live. So this is, to walk through briefly, I'm defining my sigmoid function and my sigmoid derivative. So remember, the sigmoid is the activation function. It basically turns it on or off. So I just put in that equation. So it's 1 over 1 plus, this represents e to the negative x. And then, like I said, we didn't derive the sigmoid derivative because it's a bit complex, but it actually simplifies to x times 1 minus x. So these are just functions that I'll use later. Now, and again, you'll have this notebook so you can download Azure Data Studio and try it yourself. But next, what we're going to do is create a class. And throughout this demo, we'll basically add pieces to this class. So the first thing we're going to do is initialize our model. So right now we're doing the very beginning part of that neural network. So what I'm doing is I'm basically saying, okay, the input will be X and it will be given to this model. And the weights for the first layer will be random. So here I'm just pulling random numbers in the shape of my input. And then for the second layer, I'm also going to use random inputs as well. And then I'm going to initialize a Y or an output that is all zeros. So that's what I'm doing first. So hopefully this is fairly straightforward Python also I'm going to encourage you to go back and review it later. But now that I have it initialized, what I want to do is that feed forward process. So remember, this is the process where we're basically going through the process of multiplying the weights and the inputs and adding our bias. But just like those images, I'm just going to assume bias is 0. So that plus B, I'm just not including it here. We should still get a pretty good result. But what I'm doing here is first I'm doing the dot product. Now the dot product of the input and the weights. Now, like I said, the dot product is equivalent to what you're seeing when we saw the sum of the xi times wi. So we're basically multiplying an input and a weight and then adding it to the other input and weight and then adding it to input times weight, et cetera, for all our inputs and all our weights. Now, once we have that, so that's this part, then we're taking the sigmoid of that. So that's our activation function. And this becomes the output of our first layer. We take that output as our first layer and use it as our input to our second layer. And we use our second weights, we do the dot product and take the sigmoid, and that becomes our output. So, so now we've done our feed forward part. So we've initialized and we've added feed forward. We're getting really close, so just stay tuned, hang in there with me. The last thing we have to do is this back propagation section. If you recall, what that's doing is we need to use the derivative of the loss function to find how we can change our weights to make our loss less. So without losing you, we're taking the derivative of loss of our output. And this is where that chain rule comes in. And we're using it to do the dot product with the first layer. And what this gives us is our new outputs. So basically, to just go through that one more time, is we take the derivative of the loss product, the loss, and we do the weight, the dot product with the previous layer. Hopefully we're following. But this will take some time to kind of digest this through, especially because you're missing the derivative of loss here, since we didn't quite derive that. But just trust me on that. We're doing the same thing, but one layer back to get that second weight. And then we're going to add that to our old weights. So for example, this is our how the loss function. So we're finding the derivative of loss with respect to the weights in the second layer. And then we find the derivative of loss with respect to the weights in the first layer. And that's what these formulas do. And then we add that derivative of loss to our old weights to update them. So we're hopefully moving them in a direction that decreases our loss. And once we've done that, we are ready to actually use this model for something. So if we take a look at a simple example, I mentioned this handwritten digits is a very common example for image processing. And it's a great example to learn. So if you go on to start using Keras or TensorFlow, I definitely recommend it. But I wanted to take a more simple example that we could use. So what I did, instead of doing 28 by 28, I basically did 3 by 3 images and said, can we identify which image has an L in it? So for example, this image, and this image, so image 0, 1, and 4 have L's in them, like the letter L. Hopefully that makes sense. So what I did, we talked about it a little bit, is you take the image and then you break it into pixels. So I broke it out into, pixels, very small pixels, or very big pixels, just 3 by 3. And what I'm able to do now is turn this into a number. So for example, if I wanted to turn this into a number, it would be 0, 1, 0, 0, 1, 1, 0, 0, 0. I'm giving ones to blue and 0 to white.
Anna?
Yes.
I think I personally, what I'm missing is where deep learning is applicable. So I understand machine learning is applicable. I'm trying to guess if you're gonna buy it or what's what also you can include in shopping cart. But where's deep learning applying? Well, I mean, yeah, what's the application for it?
Sure. So the application of deep learning, if we take a step back, so if we go back to here, so image recognition is something that deep learning is been widely used for. Additionally, so whether it's handwriting digits or actually text on written digits or facial recognition leverages deep learning most of the time, or even when it comes to voice recognition, this is going to be leveraging deep learning most likely. All of these complex AI related scenarios, you're typically going to get the best response from deep learning models. So these are kind of very advanced types of machine learning models that can address very complex problems. For example, I have an iPhone, and my iPhone can recognize my voice and actually authenticate me to my phone with my voice. Now, what it's doing in the back end is leveraging neural networks to create an object model that represents my voice font, is what they sometimes refer to it as. So there are lots of applications for deep learning, leveraging neural networks. And I can also, after this, I can share some resources that also share some of the like most commonly used things that use neural networks. But off the top of my head, I would say it would be image recognition, it would be, or any sort of visual processing, it would be voice. There's also been advancements in actually understanding paragraphs of text that's using deep learning. Yeah, but I can also share some resources after if you think that would help.
Got it. Thank you.
Sure. So if we look at our L example, we have, again, a few L's, and basically we're going to use this model that we created that goes through feed forward and backprop to identify if these images have L's in them. And again, these L's could be much more complex, right? It could be numbers. This could be an image. We could be trying to assess the damage on a car for an insurance company. There's lots of things that we could use this for later, but in its simplest form, let's just say, to keep the math simple and the understanding simple, we're looking at L's, and it's just a 3x3 image. So what we can do is we can basically roll out these L's. So if you see here, this is just the first row of image 0, followed by the second row of image 0, followed by the third row of image 0. And then we've turned it into a number, associating white with 0 and 1 with blue. So I did that for all this, and we were able to create a matrix or a data set. So if we look at that data set, we're able to see that the features are here, and then we also added labels. So remember, just like in machine learning, these features are the data that we're going to use to try to predict the labels. So again, this shows that image 0, 1, and 4 would be L's, which lines up with what we saw here. Image 0, 1, and 4 are L's. Okay, so now we have everything ready. Now we're going to create this neural network using X and Y. So those are the X and Y that's our features and our labels. And then we're basically going to run through feed forward and backprop 400 times. That's what this simple piece of code does. And then we're going to output our confidence in if the neural network thinks it's an L or not. So it's very quickly able to do this. And we can see that it's 98, 99, and 98% sure that image 0, 1, and 4 is an L, which is correct. And it's less sure that it's an L and you can actually flip that and say it's very sure that it's not an L. So this is a very simple example. I highly recommend reading through it. There's a lot of text and other links in here. You can actually walk through building it yourself as well, or using this sample here. So that was a lot. I know that probably I lost some of you, which I hope is not the case for a majority of you. But again, we'll talk about some ways I recommend if you want to go deeper in this, or how you can just start using it, okay? So we'll start by talking about some of the platforms and the tools that are available. So the first one I wanted to mention is the Data Science Virtual Machine. Now, this is a virtual machine that's available in Azure, and basically it's loaded up with everything you would need to start learning, implementing, or even doing like production level machine learning. There are different images or virtual machines available that do different things. Like there's one specific towards doing things related to geo machine learning or deep learning. And this is a really useful tool if you're learning or if you're just doing production data science. One of the nice things about it is that you don't pay for any of the software that they deploy on these virtual machines. You simply get to use these machines that are set up, ready to go. This is my default VM selection in Azure. And you just pay the same cost for any virtual machine, except it's set up and loaded with all these things for you to use. So that's one thing to consider. And it already has everything you need to do all the things you saw today downloaded, as well as various tutorials. So that's one tool you can use. But there are several different platforms and services that are available to make this journey to getting more intelligent insights at whatever level is required for you. So we talked about cognitive services. There are many available that are just ready to use. We didn't talk a ton about some of the frameworks and services that are available to help you accelerate your machine learning or your deep learning solutions. I know I mentioned this, but we walked through how to, from scratch, build a neural network in Python. This is not what you would do on a day-to-day basis. It's just to understand how it's working in the backend. We support all these frameworks on Azure, or you can run them on your own computers, but to leverage these libraries and frameworks that are built for doing deep learning. So it makes it much easier to follow. Then we have services that can help provide you the compute or CI/CD or ML ops that you might need. And you can even, scale up to CPU, GPU, or FPGAs, depending on what type of compute you need to do the machine learning and deep learning that you're trying to do. So at every level, we're trying to help. Now, I want to take a step back because this is very general with regards to Azure. But if we talk about SQL again, coming from the SQL world, I got to talk about SQL. I just wanted to call out how this Azure, how this machine learning services and extensibility is actually working. So what we do is you have SQL Server, and we have CLR as well. But some of the concerns we've heard around CLR is that it runs in the SQL OS. And this is concerning for people because they don't want a malicious CLR.NET program to mess with the fidelity of their SQL OS or their SQL Server. So what we did is we created this new system starting in 2016 with R. In 2017, we added Python. And in 2019, we added Java. But what this allows you to do is you write T-SQL. And what it does is we use something called the Launchpad. And the Launchpad launches satellites. So you see the theme we went with there, to use a Launchpad to launch satellites that can communicate directly with SQL Server, but it's not actually running inside the SQL OS. So that allows us to not have to move the data, but it also allows these processes to be separate. So that's what we did with the introduction of machine learning services and extensibility. The reason I have .NET here is because we're currently considering the idea and working on the idea of potentially opening this up so you could develop a language extension for whatever language you might want, like .NET or F# or what have you. So that's how this kind of works, and obviously there's a lot of benefits to using SQL Server and Azure SQL. I won't harp on that too much. In Azure SQL Database, currently there's previews for support for R in SQL Database. There will be upcoming announcements in the future, which I can't talk to you yet, but we will be working on extending these machine learning capabilities that are all available on SQL Server today into our Azure SQL space. And then finally, another thing about SQL is that you can kind of train and deploy wherever you need. So if you need to train on-prem and deploy to the cloud, SQL can support you. If you want to train to the edge, deploy to the edge, we also have Azure SQL the edge, so you can do it at the edge as well. With big data clusters, you can do it in containers running on Kubernetes. The options here are really kind of endless. Big joke I have is trying to understand what each of these icons mean. I think I've got most of them, except this last one. I think it's, IoT, like smart cars, smart factories, your wearables, construction, in your chips, having smarter chips or deploying to chips, or vision, and I'm not sure what this one is. If anyone has ideas, I'm open to that. So yeah, I hope this was really useful. I have some resources. I can skip the pop quiz unless people are feeling especially interested in coming off mute. Otherwise, we can just kind of walk through them as a review. So data science is the analysis we talked about of analyzing data, but using that scientific method or the scientific process. The team data science process is a recommendation from Microsoft that allows you to walk through all these steps and how it relates to a team. And artificial intelligence is really just this idea of getting computers to mimic human behavior. So things like speech or vision or reasoning. And machine learning is a technique for being able to make predictions from data. Neural network is a common machine learning technique. And we talked about how a deep neural network is a neural network with multiple hidden layers, and sometimes many of them with different combinations of various things. And hopefully you also saw that Azure and SQL Server can be of use in this space. Now, some resources for you. I can actually share these so you can navigate, and then let's see. So the first one is aka.ms/SQL workshops. So if you go to this, Bob Ward, Buck Woody, and myself have been working on this for a while. But what we've done is we've created these workshops and materials that you can use in person with your customers, with your team, whatever. They're all out here. You see we've got some stuff for R and Python and machine learning, as well as other tools and presentations from people like myself or other people from the SQL community at Microsoft. So that's available. I definitely recommend checking out this machine learning one if that's something you're interested in. The second link that I'll put back up is aka.ms analytics. So it's like analytics, but with two N's because my name's Anna. I think I'm very funny. And if you go to that one, you'll be brought to all the presentations I've done on SQL. This one specifically is from past. So this was where I first did this session. But if you go in there, you can find those 3 notebooks of what I did. You can find the slides I went through today. And yeah, if you have any comments or feedback, I'm always happy to take them. You can reach me on Twitter, or this is my email address. I want to thank you all very much for joining, and would love to open up for questions or discussion or anything else.
The one thing that occurs to me, assuming you guys can hear me,
Yep.
when it comes to the whole data science, big data, analytics, Microsoft offerings, it seems like literally every week there's something new, and trying to even keep track of what they are, let alone how you best to use them, it seems almost like it's a full-time job in and of itself. And for those of us who've been, living mostly in the SQL Server world and thought we were hip and cool because we knew how to do SSRS, SSIS, and SSAS, and here you've got, 30 different things, and it's what's the best way to get a handle on this and to know what it is? Because everyone wants, oh, well, we need you to know big data and data science and data analytics and data engineering and all this stuff. And it's like, it's all over the place. So I don't know if that's a actionable question, but there it is.
Yeah, I mean, I think it's something. I definitely see where you're coming from. I mean, personally, it's always a challenge to keep up with the latest stuff that we're doing, let alone what other data-related teams at Microsoft are doing, let alone what other companies in the data space or cloud space are doing. So I think it's always going to be a challenge. I think one of the benefits of learning the technologies related to SQL, especially for data professionals, is that SQL isn't going anywhere anytime soon. So the technologies that we invest in the SQL space, at least, you can expect that they will stick around for a while. If that's any consolation, I don't know. As far as just general big data and machine learning languages, I think as we move forward, it's going to be increasingly important for data people to understand machine learning. Now, yes, learning all the different technologies, they're changing very frequently, but I think to understand basics of how these methods are working, so how, like, what these different things are, what it is when we say machine learning versus deep learning versus artificial intelligence versus doing analytics on Spark versus in database machine learning. I think it's going to be important for us to understand at a high level the landscape, but for things I would focus on, like I think picking Python or R and getting okay at it is not a bad idea because they have the extensibility into SQL, but they also are very predominant basically in all the other technologies today. So I know that's not like a great answer, but I feel your pain, and I think it's just something we're all going to have to keep working on because the landscape is just going to keep evolving like this.
Anna, what would you say is a good place to start if I wanted to learn Python? I've been just jumping around from one thing to another, kind of, YouTube and Udemy, but is there a good resource for someone who's a beginner?
Yeah, sure. So there, it depends. Like if you want like the 101 on Python as it relates to working with data in SQL, this first link, the SQL workshops, there's a Python workshop there, and I think that would be a good start if you're really trying to get up to speed with Python itself. I like DataCamp, and I like edX, so edx.org. Data Camp is nice because it's all kind of interactive. I'm not sure if you've seen that one, but there are lots of tools out there because a lot of people want to learn. I would also recommend, once you kind of get a handle on it, to check out something like Kaggle. It's something I mentioned before. I can put it in the chat, but Kaggle is basically somewhere where they have a lot of free data sets, and just to kind of pick a data set and work through like a data science lifecycle type of thing, identifying the problem, understanding the data, and then going through a machine learning thing. I think that's valuable too. A lot of this monkey see, monkey do, like you're not necessarily really, might not stick with you as well. I find like struggling is the best way to actually learn some of these things. And then, there's also opportunities to, like I mentioned at edX.org, I use that. A lot of the courses there are actually free. It's just if you want a certificate, you have to pay. But for me, if you just want the learning's for free. So I really like those, and they have programs from universities like Columbia, Georgia Tech, Berkeley, that are all pretty good.
Thank you.
Let me ask you one question. So, in order to learn and master the machine learning, right, should one be exceptionally good in mathematics, or need a sound knowledge in mathematics?
I think it's important to understand the basics behind the math of how these things work. But in my opinion, it's once you get those basics down, it is no longer rocket science. A lot of the libraries are available for you. There's a lot of packages that have all the algorithms. They've worked out a lot of the difficult part of implementing some of these models or algorithms, whether it's machine learning or deep learning. So I do think that you need a basis of math, but you don't need to be like a stats master's student or anything like that.
Thank you.
Any other questions?
Hey, Anna. Any recommendation on boot camps or crash course where, like, few days, like we work on it, like 8 to 5? Do you have any recommendations on that?
There is one that I know of. I'm trying to think of the name of it. I want to say it's called General Assembly, but if you shoot me an email, I can find out exactly what it's called, but I think it might be General Assembly. But there's a few programs. There's also if you shoot me an email, I'll send you. There's two I have in mind, and I don't have the names of them off the top of my head, but I'd be happy to share them with you. One of them is like yeah, great. One of them is like a 9-week course, I believe, that's like 8 to 5, and then at the end of it, they help you find a job, and you do have to pay upfront. And then the other one I'm thinking of, and I'm trying to think of the name of it, and it's just leaving me, but there's another program that's actually free until you get a job, and then once you get a job, then you pay like a certain amount for 1 or 2 years or something like that. So there are ways to, if you really want to like drop everything and get a job doing data science, there are certainly avenues to do that on a pretty quick timeline. You might also consider doing something on the side. For example, I am working on a master's degree on the side online from Georgia Tech. And it's fairly inexpensive. It's a lot of work, but it's worth it. But if anyone has questions or general advice that they can't think of today, or I don't come up with an answer, like feel free to shoot me an email. I'd be happy to help any way that I can. Yeah. Cool. Cool. Well, if there are no other questions, I will pass it back off to you, Steve. Thanks again. This has been a great opportunity for me, and thank you guys for spending your weeknight to hang out.
Thank you for an excellent session.
Thank you.
Yeah, thank you, Anna.